All right, okay. So let's start with, what did we talk about last time? Oh wait, this is so nice. Last time, we talked about spin stuff. With like because spinors and spin geometry is sort of the underlying, what supersymmetry is built on top of. So essentially, we constructed a spinor representation. For everyone's favorite Lie algebra, which is the SO2, 1, which we're thinking of as the rotations of three-dimensional space, three-dimensional space-time, two space dimensions, one time dimension. And we realize that there's actually an isometry between this and, sorry, an isomorphism between this and SL2R. And we constructed the spinor representation is a real representation, two-dimensional representation, which we call S. And in fact, in this case, it's very explicit what this is. This is just the standard representation. I have a 2x2 real matrix. It acts on real vectors. But the way we constructed it is using this a whole lot of machinery about Clifford algebras. So what we did is we started with the Clifford algebra, sort of based on the vector field R2, 1, where you take the it's the algebra generated by vectors in R2, 1, where you essentially wedge them together. That gives you the underlying vector space. So the underlying vector space of this algebra is the exterior algebra. And the product, we have an extra condition on the product, which says that if I take a vector times itself, a one-dimensional vector times itself, then what I get is not an order 2 element, not the wedge of those vectors, but a single real number, which is the norm of that vector. So we write this as the exterior algebra of, we write this as, let's say, something generated by basis vectors E0, E1, E2, modulo relations that basically they all anti-commute and they square to 0. So, and then a compact way to write that is EI, EJ is equal to like delta IJ times norm EI, EJ. So if I does not equal j, they anti-commute. If I equals j, you get the norm out. And inside this Clifford algebra, basically we have a natural representation in terms of S. But what's important about this is we get an action of V on the Clifford algebra. So your vector space R2, 1, which sits naturally inside of the Clifford algebra. CL, I'm just going to write this as 2, 1, because we're R2, 1. Our vector sits inside, and we can use that multiplication by this vector, because basically this spinor representation comes from SO2, 1, but it's induced by multiplication in the Clifford algebra. So since we can think of this every vector as sitting inside the Clifford algebra, we actually have an action of R2, 1 acting on S just by Clifford multiplication. Sorry, wait, did I get this right? Let me check.
This anti-commuting thing, like it only works for I and J, not like you have like EI squared is the norm. Not like
so EI squared, so that's what this says. It's EI squared is equal to, so EI times EI is equal to norm of EI.
or like what can't isn't it EI plus EI.
Yes, exactly.
So like we only want EI squared.
So I guess so EI plus EI. You're saying that this is equal to 2 times EI?
So that's 2 EI squared. But last time we did, like you said EI squared.
Okay, so let's go back. times 2. Or multiply by 2. Thank you. 2 delta by 2. So what I discussed last time was that there is a, hold on, let me find it. Make sure I'm not making a fool of myself. We had, yeah, V acts on S by the Clifford representation. But basically we can turn this representation into a pairing. We can just sort of rewrite it in tensors in fancy ways to get a pairing. Gamma, which maps S dual tensor S dual to V. So again, there's more details about how this pairing actually comes about. And to get that pairing, we're using in a vital way this fact that for this real representation, a fact that's true is that it's isomorphic to its dual. But the point is you should think about this pairing as originating from multiplying by a vector. Taking a vector, thinking about it as a Clifford algebra, acting on it by the Clifford algebra. Clifford multiplication by a vector is sort of the origin of that pairing there. So the sort of punchline I had from last time was that this the punchline is that in 3D, in our situation here, we actually have an isomorphism. Yeah, V is isomorphic to symmetric square. So the tensor of S dual, the symmetric square of S dual, that's S dual tensor S dual, but symmetrized as a tensor. And this is the motto that spinors are square roots of vectors. So first square root from this supersymmetry business. Spinors are sort of constructed as a square root of the usual, the spinor representation is a square root of the usual vector representation. Now, again, I want to be careful. This is only precisely true in this exact sense in 3D. But in general, you can always decompose a square of spinors into a vector. I guess a vector, the standard vector representation always contains the squares of a spinor representation. So there's always some form of which this is true, but in our case, it's more precise. Okay. This is a quick review of last time. How are we feeling about that? In which case, let's move on to this time. So if I could have someone be the professional. Well, there we go. Okay. This will be my standing chair. Okay, let's go. So let's start by, yes.
Question. So
Absolutely.
I think we claimed that S is like a real structure on the complex spinor representation.
Mhm.
Did we know like why that was invariant or like why the Clifford algebra?
Right. So last time we were sort of, we had this big debate about, why, like I claimed essentially that you can build S as a real representation by sort of starting with a complex spinor representation, which is canonically defined, and canonically defined by the isomorphism CL2.1 is isomorphic as an algebra to 2x2 matrices. And I said, look, that has an obvious complex representation. We can find a real representation inside of it. And I claimed that I would figure this out and tell you this time, but I haven't figured it out, so I'm not going to tell you this time.
Okay.
Sorry about that. I think what might be going on is that, like, yeah, I don't know. Same issues as before. Okay. Sorry about that.
So what do you mean you get an action R21 and something CL21?
So this is an embedding into CL21 because CL21 is based on the exterior algebra. So the embedding is given by just taking these vectors. So this is sort of the natural way. We're building this by sort of taking these vectors. Building this by taking these vectors and taking these vectors and sort of multiplying them together and seeing what we get, right?
So the action is of S on R21.
So we have R21, it's sitting inside of CL21, and S is a representation of SO21 that comes from a representation of CL21. In particular, every element of the Clifford algebra acts on S and preserves S.
Okay.
And since these are inside the Clifford algebra, we get an action of them on S. This action is coming from essentially just
Okay.
multiplication. Clifford multiplication in the Clifford algebra.
But where's the pairing come from?
The pairing is just roughly, the pairing says that, so we have this action, we can think about this action as an element of, I guess, it eats in a vector and a spinor and it spits out a spinor. So we can say that it takes in 2,1, answer with a spinor, and sends that to a spinor. And the idea is we move one spinor to the other side, move R to the other side, and then take duals as C fit until you get something that looks like this. I said a V, I should have said R2,1 in this case. This is basically taking this action here and rearranging it because it's linear, so you can write it as a map of tensors.
I think about this. I'll come back to you.
Okay. But we will be basically this pairing is telling us that we can combine two spinors and get a vector. And that's ultimately what it's saying. Okay. This time let's talk about supersymmetry. So we have the super Poincare algebra, which I can now describe fully. The idea is, this is a supersymmetry, an extension of the Poincare algebra, which was ISO 2.1. We're extending it to be a super algebra. So let's see what we get. We have the even part and the odd part. And the even part is just going to be the regular Poincare algebra, ISO 2.1. And the odd part is going to be, I said at the beginning that the odd part, this is a physics thing. It's called the spin statistics theorem. But from physical input, we get that the odd part has to be, if you remember that, if it has to be some spinor representation. And in fact, we get that it's the direct sum of some quantities of these spinor representations. Okay. I'm going to call this guy a fancy n. That n is going to count the number of these representations. Remember that the action of G0 on G1 is an element of G1. So naturally we have that G1 is a representation of G0. Okay. Yes.
So you used the definition of theorem. Like you said something like something has to be a sum of.
Yes. So this is let's call this a definition. Mathematicians, we're going to call this a definition, but physically this is a factor which we derive. And we have to derive it from the axioms of quantum field theory and stuff, and it's really annoying and not in the scope of this. I don't really honestly get why this is true physically. But basically, in our context, we're defining the super Poincare algebra to be such that the even part is the Poincare algebra, and that the odd part is some direct sum of spinor representations. But in physics, this is not something which you assume. This is something which you kind of derive from the principles of quantum field theory, that it has to be this way.
Okay.
Okay, awesome. So for example, basically we have different names of supersymmetry. So when people talk about this fancy n=1 supersymmetry, this is like what they write down. They write down n=1, and this says that G1 is just equal to a single string copy. Yeah.
So you have defined everything. Is just only tell us the product on G1. right?
I need to tell you the products, absolutely. So I'm telling you, this is the underlying vector spaces. I'm gonna put the products over here. So this is just the terminology that you might see. You know, people talk about n equals 1, n equals 2, n equals 4 supersymmetry. They mean the number of copies of the spinor representation, the size of the odd part. Okay. So that's the vector space. So this is the that's the vector space here. And let's put the bracket structure over here. So first off, we have the bracket structure entirely in the even part. So recall that the isometry 2, 1 is equal to the semi-direct, basically the direct sum of rotations around a point and translations. So we're going to choose generators for all of these bad boys. So we're going to choose a generator J inside of SO3. We're just going to kind of symbolize J represents an element of SO3. P represents an element of R2, 1, and Q represents something in the odd part, which is an element of one of those spinor algebras. This is just schematic right now. And what we're going to do, first I'm going to describe the even part. Is going to have, well, SO3 stays within its own realm. So J, J is an element of SO2, 1. And rotations and translations mix. A rotation acting on translation gives another translation. So their bracket is in R2, 1. And translations commute with one another because we're staying entirely inside this abelian Lie algebra, which is 0. So this is the just the bracket structure for the standard even part of the Poincare algebra. Okay. Odd stuff. So we have that P commutes with Q. And we sort of have by definition, Q is a spinor representation. This is because the representation Q is a representation of SO2. And then it's sort of the trivial representation in R21. It doesn't do anything. So P acts on Q trivially, and the rotations act on Q by another rotation. So basically, and the rotations act on Q as you would in the spinor representation. So this is the standard spinor representation. And finally, we have the bracket, which in this case I'm going to write as the anti-commutator because it's between two odd parts, so we get the minus sign shown up. Q, Q. And this is going to be, if I call them Q1 and Q2, what I'm going to get is I'm going to get a vector. And the vector I'm going to get is I'm going to use this pairing over here that we built up to. So it's going to be equal to gamma on Q1 and Q2. Okay. How do we feel so far? Yes.
That works. What if I have multiple spinners?
If I have multiple spinners, so if I have one spinner, so this is n equals 1 bracket structure. If I have n equals 2, then, or some larger one, then let's see what we get. We have the same relationships for the even part, because our even part's the same. Let's denote as tensor, let's call this the I part or something like that. So this is 1, we're just going to call these the indices. So this is Q1 and Q, n equals little n, Qn. Let's do like that. I don't know. I don't really know how to denote this nicely. And basically we can add, we say that Qi, Qj is equal to 0 when not equal J and equal to gamma. There we go. Essentially, the different parts don't mix together. And spinors act on their own thing, as you would expect. It's a direct sum of representations. It's that representation. And brackets between each other don't mix. Except you do get an extra thing showing up. An extra symmetry called R symmetry that acts only on these guys. Essentially, this is, so R is an endomorphism of S to this vector space. Essentially, that is, I guess, invariant under J, probably. So this is, this is asymmetry, but it's not an explicit part of the supersymmetry algebra, I think. I don't know, it's a little unclear. But basically, we get that our Q is an element of the odd pair again. So let's see what we have here. Step back a little bit. R, so for example, R could be, if this is a matrix. So let's say we take two of these. We can think of R, for example. A common one is R equals U1. This is so U1 symmetry, which rotates this space, say these two elements there, we rotate them by just having a rotation matrix, cosine theta times identity, sine theta times identity, so on and so forth. But basically that just takes these two elements and rotates them into each other. So these are basically, we need that R preserves all of these subspaces, right? But the R symmetry is going to be symmetries amongst these subspaces, relating them together. Yeah, John?
Should that be a direct sum or a tensor product?
Let's do direct sum. Thank you. That is much better. Okay, because like if I write an angle, there's a sort of a one parameter family interpolating direct sums and direct products as they go from 0 to 45 degrees. Yeah, thank you. So I'm going to actually, so the R symmetry, e.g., for example, this could be a U1 symmetry.
You mean you're rotating each spinor by the same amount?
Who asked that? Yes. No, I think what I'm saying is that each spinor is being rotated into one another. Basically, we have these two two-dimensional spaces. I know these have to be preserved by wait, sorry. I know that I have to send blocks to blocks.
Right, okay, that's the.
And what I'm doing is I'm taking these basically, I separate it into this 2x2 block, because each of these is 2 dimensions, remember in our case, 2x2 block matrix, and I'm kind of rotating one block into another block. So these are symmetries within the odd part, entirely within the odd part. That's what we're looking at.
Okay, so this U1 thing only works for n equals 2.
This U1 thing only works for n equals 2, but for higher n, you get UN R symmetries.
R is the. Okay.
So e.g., n equals 2 implies U1 symmetry. Let's say that. Okay. So this is going to be important later because R symmetries are once you get onto your moduli space, once you get to Coulomb branches and stuff, R symmetries are going to give us extra geometric structures on that moduli space. And they're also give you like fancy dualities and stuff. So these are very important, but for the structure of the supersymmetry algebra, they're somewhat incidental. Yeah, Eric?
Two quick questions. One, this connotation of like bracket RQ, is that just like R as an endomorphism acting on Q?
Yes.
Okay. And then the like curly braces you have for like QI like that,
Mhm.
that just seems to me like it's the same like super bracket but on the odd part.
Same exact super bracket. I'm writing it as a squiggly brace so that you remember it's anti-commuting on the odd part.
Okay, great.
Exactly. Okay,
Can you just say again what R is supposed to be doing? I'm just not sure I
Okay.
understand from what I mentioned.
yeah, so. R is essentially, we can think about it like this. I might be getting the details wrong because I am winging this R symmetry part a little bit. But what is R supposed to be doing? R is an internal symmetry of the odd part. It is internal in the sense that it basically mixes the odd part with itself. And it does not involve any even things showing up at all. So basically, say I give you two supersymmetry generators, two supersymmetric things, two things in the odd part. And one thing I can do is I can try rotating them. I can try rotating it by essentially a complex number. And something that we can say is that, like, we can think about n equals 2 supersymmetry. This is rough. So heuristic. In n equals 2, we have that S star, tensor S star, is kind of ish isomorphic to tensoring of C. Right? We can think about that as like real and imaginary. And this U1 symmetry I'm describing is multiplication by a complex number, rotating the real part into the imaginary part. Here, so make sure I'm not
But
being
that's actually
confused.
literally true as representations of
It's
S.
not literally true.
Well, if you take them as one of the right is a trivial representation. And this is literally true.
Oh, is this a?
Right, like you think of C as a two-dimensional trivial representation, that's it, this is literally true.
Okay, okay, so we can think about this literally as representations. That's good. So the point is that the R symmetry in this case reflects. I could just kind of get that corner over there. Yeah, so the R symmetry reflects. It lives in here. And in n equals 4, we have S star plus S star. We have 4 of these guys. And we should kind of think about this as a star tensor with quaternions. In which case the R symmetry is going to be, I guess, S3 or something, some quaternion preserving thing. We're going to come back to this later because this is an analogy right now, but it becomes precise once we start looking at representations and stuff like that. But n equal 2 supersymmetry is really a complexification of normal n equal 1 supersymmetry. N equals 4 supersymmetry is a quaternionization of n equals 1 supersymmetry. And this structure, again, associates to all of the geometry that we're going to get out of these supersymmetry algebras. They're going to give us quaternionic, complex and quaternionic structures on our moduli spaces. When in my Linau class today, I had the kids who saw me doing that and they all were trying to practice it for the last few days. So I had a competition at the beginning. Whoever could draw the best dotted line got the gut eraser on the board.
Did you win?
I did win. I get the gut eraser to myself. No, I did not. I gave it to the best group. One person like drew their name on it. They like wrote letters and stuff. It was really impressive. Anyway, okay. So let's go. Actually, let's just go. Okay. Supersymmetry algebras. Lots of fun. Everyone's enjoying them. So remember last time I tried to sort of frame this as supersymmetry is, a bunch of, it gives you square roots of familiar objects. This one gives us a square root of another familiar object by this option here. Remember, the anti-commutator of the same thing twice is going to be a, just the object squared. So this is saying supersymmetry squared is the pairing of those two things, which is a vector. Supersymmetry squared is a vector, and we can see that in the motto. Supersymmetry is the square root of translation. We can see it on the algebra level here, but let's see that something more precise. So, the idea is we need to represent our supersymmetry algebra. We want to represent this as an action on some space. This will give us basically realizations of what the supersymmetry actually looks like in terms of, how it moves stuff around. Because, for example, remember, we defined the isometry group. This Poincare algebra here, we defined that as the Lie algebra of isometries. So motivation. The isometry group 2.1 is isomorphic to the Lie algebra of isometries on R21, which means it comes with a built-in action. So the space that we're considering is this. This is going to be R2.1. And if we have a point here, there's two parts of it. We have the R2.1 part, which translates that point around the base. And then we have this SO 2.1, which rotates that point. So, the built-in action is actually on a coset space. The action is on the Poincare group modulo the stabilizer of a point, which is just rotations around that point. And this is like R21, but it's actually like, it's not quite R21. It doesn't have a group structure anymore. It's just a symmetric space. There is no origin anymore. We're just thinking of nice flat space time. That's the base space of our action, the Poincare group. Okay. So now we want to extend this to supersymmetry. So we introduce n equals 1 superspace. Oh yeah. So this is going to be, we take we're doing this again heuristically, we can think of it as a coset space. So we start with a super Poincare group, which is again some supergroup, which I haven't defined, but you can imagine this exists. Some supergroup whose Lie algebra is the is this thing we've been considering the super Poincare algebra. And then again, we mod out by SO 2.1. And then the question is, what do we get? Here's what we get. We get an affine space just like above, but remember, we're basically killing off all the rotations, but we still have the translations and we still have this S over here. So it's based on a super vector space, which I think this is the notation that Eric used. It's based on a super vector space, which has, and the even part, R2.1, and as the odd part, the spinor representation. Spinor representation because we're in n equals 1. And to remind us that we're in the odd part, we're going to use this parity change operator here. That tells us we're swapping that from even to odd. Okay. So importantly, this is kind of weird. There's something weird going on. And the weird stuff has to do with parity change. We're switching it from even to odd. Yeah, John?
So when you say super Poincare, you're meaning some sort of super group?
I mean a super group, yes.
So it's a manifold with an extra,
Manifold of a superstructure, but it's kind of weird to define supergroups because we haven't defined a supermanifold yet. Because to define a supermanifold, we need a notion of super Euclidean space to base on, and that's what I'm defining right now. So that's heuristic. But it's based on a super vector space. But what's important about the super vector space, what really gets our juices going, is the ring of functions on this space. Because I know that this is like a kind of an algebraic geometry group here. So I don't know algebraic geometry, but I can pretend to talk about algebraic geometry. And I know you guys love rings. So the ring of functions is gonna be smooth functions on the real part. So I don't know, it doesn't really matter. Some regularity functions on the real on this nice even part that we know and love, times the exterior algebra of S dual. Yes.
Here, for the built-in action, are we like exponentiating the Lie algebra?
So the built-in action is basically, we have an action of the Lie algebra of every element of the Lie group gives us a map from our space to itself. We can differentiate that to get a vector field. That vector field is sort of the infinitesimal action. Yeah.
could you want tensor of exterior algebra there?
Thank you. See, as I said, I don't know what algebra is, but I can pretend to.
Like, what do you mean infinitesimal action?
So, so I said a built-in action on, what I guess they really mean is, a representation where I take, you give me an element of the Lie algebra, say translation in the x direction. I can represent that as a vector field, which is the vector field which points in the x direction and is constant everywhere. So a representation from ISO 2,1 to vector fields on R 2,1.
Okay.
That's the infinitesimal version of an action. So this is the ring of functions. So in particular, there's this, functions that you get, functions you understand, functions that are familiar of just, I have some function on R3, R21. And then there's this other part, which is weird because these are nilpotent. So I can actually describe this explicitly. This is like the Grassmann algebra. So if I have C of theta 1, comma theta 2, where theta 1, comma theta 2 is basis of a star. So I start with basically two things that are two things in the basis of the spinor. This is a vector space. I choose basis vectors, and I'm going to mod out by the Grassmann relations, the things that give me the exterior algebra, which are that everything anti-commutes. Theta I, theta j equals negative theta j, theta I. In particular, theta 1 squared equals 0. Which is weird because you can't, in normal space, there are no functions which square to give us, to give us 0. If you square a function and a function's non-zero at a point, that's still going to be non-zero at that same point. So this is something which you cannot, which you kind of have to have you need to change your intuition on a little bit. So so I tried to kind of, this is the sort of thing which you can try to represent with a picture. So here is, so we have this ring of functions, which means that we get as a consequence that the actual space itself is defined to be the space whose ring of functions is this. So it's going to be defined to be equal to spec of, and since we're in algebraic geometry now, we're going to replace this with rings of polynomials. So C of x0, x1, x2, all number simply variables, hence the exterior algebra of S. Cool. So what does this look like? Here's how we can think about it. So the only sort of, yeah, John?
What do you mean by spec here? Because spec is traditionally only defined when things are commutative.
Is that true?
So if you're looking at like a super algebra, like this is here, then the spectrum has an underlying topological space, just the spectrum of the reduced part, so you quotient by all the odd sections, and you just have that like C adjoin of x0, x1, x2. And then the ring of functions on this like ordinary topological space is this sheaf of like super rings, super algebras.
Okay, thank you. So here's how we can try to visualize that. So here is our little map of superspace for the sake of the video. Okay, so we have this underlying space is, as Eric was saying, all of the points in the underlying topological space are just R2, 1. They're the usual vector space here. But what we're doing is we're sort of adding fuzz to it, where we can think about this as extra information that is not that our functions have, that our functions carry at these points. So it's not functions on R2, 1 times the exterior algebra of S dual. It's not like that would be like sections of a cotangent bundle, sections of an exterior algebra bundle over our space-time, right? But we're not looking at that. We're looking at something that approximates that. And this fuzz over here, this sort of fuzz represents the fact that we're allowed to remember one derivative in that in this space over here. We're allowed to remember one derivative because basically we're saying that we're looking at functions where we're looking at only the point at the center. So we kind of have this bundle structure going on, but really the only points that actually matter are the ones in the center. We're having some information of how it behaves around that point. That information is captured in the derivative of the function along your spinor direction. So we're remembering a little bit of extra information. So our functions are like ordinary functions on R2, 1, carrying this extra information of how their derivative moves, of what their derivative at 0 is in the spinor bundle. That's a rough intuition about what superspace actually is. You know, it's this idea that we're sort of taking ordinary space, this is the base topological space of your ring, of the spec of your ring, taking ordinary space and adding some fuzz to it, some extra information that's contained inside the functions. Okay, how do people feel about that? Awesome. So what I want to do is I want to, I guess I should save this till after the fold, but we can actually use superspace to get a similar representation of, we're going to basically use it to get a representation of our superalgebra in terms of J and P, but also Q as differential operators, as vector fields on this space. And once we do that, then we can represent supersymmetry. We have a representation in terms of functions because we have differential operators acting on functions. And these representations in terms of functions are sort of the building blocks of how people actually interact with supersymmetry, is by considering these superfield representations.
So are you saying this is like a space of fields?
This is not quite a space of fields. This is the space that the fields live on. The fields are functions. So I guess spec of the space of functions is kind of like the space of fields. Well, sorry, that's the space of fields and they're functions on an underlying space. Okay.
Why is it C infinity up there? There's like polynomials.
So this is And it's kind of just to make algebra people happy. I don't really, I guess it's like the affine space of A1, for example, is defined to be spec of the polynomial ring of over one variable. And the functions on that space in algebra land are polynomials. In smooth geometry land, you're in a different category. You're going to be looking at, arbitrary smooth functions. But it's really just two different ways of looking at the same space. I guess. Eric?
I can comment on this a little bit. The ring of functions on this vector space, the thing with even part or two and odd part, a stool that can be generalized just like any PQ dimensional space where P is even dimension, Q is odd dimension. That RPQ is a local model of these smooth supermanifolds, which is what that C infinity business is up there. And then algebraic category, you can take spectra of super rings, and if you take spectra of certain kind of super algebra, you can get a smooth super domain. That's kind of how we're seeing here. But yeah, it's just algebraic versus manifold type category.
Let's put a name to this just before we all go off to tea. I'm going to call this space R3/2 because the real dimension has dimension 3 and that stool has dimension 2. So this is the more modern way of looking at it. Instead of talking about n equals 1 or whatever super algebra, we just define what is the dimension of the odd part of the vector space. And this is something which is easier to think about in higher dimensions and stuff. But because people talk about n equals blank so often, I want to confuse that dimension. But this is the space that we're talking about here. Okay. Awesome. Let's get some tea.
Thanks a lot. I'll have to sign off for the second part because I have another meeting, unfortunately, but that was great. Thank you.
Thank
See
you.
you next time.
There we go. Okay, so we can get Carlos' facial reaction. That's the sort of, how sometimes in video games they have a streamer in the bottom, it's gives a shock face when something shocking happens. That's your job.
Okay,
Carlos.
great.
Okay, so now we'll have to erase the Genus 2 wizard monster, unfortunately. So give a sad face, Carlos. Thank you. So let's recall where we're at. So we had this thing. What we did is we looked at superspace. Superspace is basically saying, look, I have a super algebra, and I want to represent this algebra in terms of actions on a space. It's built off of the Lie algebra of isometries. So it's built off of the Lie algebra of isometries of three-dimensional Minkowski space. The Lie algebra of isometries we can think of as the Lie algebra of the group of isometries. This has an action on the space. We can get an infinitesimal action, a representation of the Lie algebra in terms of vector fields. And the question is, what space does the super Poincare algebra act on? And the answer is superspace. Basically, a space with the ring of functions that looks like smooth functions on R3, tensored with the exterior algebra of your odd part, your spinor bundle. So we have basically defined our superspace here, our R32. We've defined that to be, the spec of this ring, and it's a non-commutative ring, but you can get it to work, says Eric. So this is where we're at. Cool so far? Awesome. So let's go to the wizard board and let's keep talking. So now we have an action on superspace. So yes.
Is there a way to get maybe I guess this is a quick part. Is there a way to get the spectrum stuff to work by looking at this as a DJ algebra?
Probably.
Okay.
It's you can just think about it you have if you're just thinking about prime ideals in this as just a ring, then prime ideal has to get all the encoded. And all the odd factors are already encoded. So any prime ideal will just exactly correspond to prime ideal of this reduced as well.
I-
I don't know if that
I-
answers the question, but.
Sure, okay, we'll talk now.
So we have, okay,
You're asking multiple things that they want some kind of.
Yeah, no.
Yes,
Obviously,
yeah.
that's a direct differential.
Yeah.
Like, but so could we just think about that thing as a spectrum of dB algebra, like, think. There's a functor of points and something instead of like the, instead of like the regular commutative algebra category, which is the dB algebra category.
okay. So, once the voices in my head stop talking about algebra, no, it's great because these are the questions that I can't answer. So it's wonderful that there are people who can answer them. So this is good conversation. I love this. So we're essentially looking at the action on superspace. And the idea is, as I was mentioning earlier, we can represent the Lie algebra of isometries as vector fields. For example, if I have my isometry Lie algebra, maybe I take P1, translation in the one direction. I sort of represent this as the vector field partial x1, right? Which in fact furnishes a representation in a technical sense of isometries of the Poincare algebra acting on functions. Right? Because every function I could just take its derivative along my given vector field, right? And this is, the representation we're looking at. So now let's give actually a schematic of what this looks like. So we have a little table here where we have three parts of our isometry, three parts of our thing. We have SO2, 1. We have R2, 1, and we have the odd part of the Lie algebra. So these are our three algebra parts, and I'm asking what vector fields these go into. So let's start with just the usual case, the one we're familiar with, non-supersymmetric stuff. So like I mentioned before, we have a representation of the translations P as partial derivative in the ith direction. Okay. We have rotations. Rotations act by rotation vector fields, and I can write those vector fields like this. xi partial j minus xj partial I for all I comma j. That where I does not equal j. Okay, and this is, so do people see why this is the rotation vector field or awesome?
For SO3, that's what they're saying. For SO4.
Right, I need to use the metric somehow. Let's do that.
So it's something like plus and minus.
So you're just replacing one of the pluses with minus. Cool with this?
Wait, no, the indices should be on opposite ends for
Yeah,
the
you're right.
variables.
To make everything line up. Let's see how do we do this. So xi partial j.
Well, but the I should be on top.
Yeah.
Like that? Yeah. That's ji, and then I want to choose this minus sign based off of the sign of my metric. So I'm going to do plus eta, and let's replace that j with a k and make that jk or something like that. Is that okay?
The I is still.
So right now we have I is on the bottom. Okay,
It was
so
funny the way it was recorded, like moving something to see up and down.
okay, so but I do okay. So let's do like this. Let's do it the way God intended. X. This is a vector, and we're taking the cross product as a gradient vector. Okay, are we happy? Okay, let's write this in indices. So basically we have X, like the actual form of this doesn't matter so much. It's more so just seeing that we do indeed get this as a vector field, for our peace of mind. So xi partial j minus eta, I guess the i's and the j's, minus eta, where eta is replacing I with, is basically doing your metric for you. And then I guess, I don't know, ik, xk, partial j, or something. And let's do modulo, up, down, tensors, indices.
Vectors should contract.
This is contracting with the x.
I think it should.
Contract
Is
both
that
of these
right?
together.
Yeah, is that all right? Because you want like.
Well, so this is basically a Dirac delta, except it has a minus
Oh,
sign
yeah,
in one of the
different
things.
one, that's right.
So this
Sorry.
takes the x and makes it a lower index xi, except it has a minus sign in one of the coordinates. That's just what we need to get it to be indefinite metric here. Okay. Okay. Oh, now we get the real challenge. How do we represent supersymmetry? And the thing about supersymmetry, we don't. Like, this is not applicable. So this is the even part, which exists, which is basically ISO 2,1. And let's now ask.
Wait, aren't these acting on R21? Not SO21.
Yeah, so these are acting on R21. So this is the representation of ISO 2,1 that sends. So this is a map from ISO 2,1 to vector fields on R21. Okay. So now we're going to do the same thing, but supersymmetrically, and we're going to see how things change. Again, I'm not deriving this, I'm just kind of saying what the answers are. SISO, I kind of mixed this up, and I'm representing that as, now I'm looking not at vector fields, but I'm looking at super vector fields. Woo. Okay, so we're looking at vector fields on the super algebra. What do these look? So what do these look like? Well, I'll tell you. This one is just exactly the same thing, because remember, supersymmetry does not do anything on. Supersymmetry doesn't do anything on the supersymmetry part, right? The commutator to 0, which means that this is the same thing. So it's translation on the, I guess, the even part. But rotation, remember, so just for the folks at home, translation doesn't affect the supersymmetry. Rotation does, though. So I can write it as follows. I keep the same description as before. Xi partial j minus eta I k xk partial j plus a rotation on this guy. And remember, I have coordinates for this coming from the theta I. So the rotation is theta b partial over partial theta b minus theta a partial over partial theta. Sorry, alternating. Theta a and theta a, theta b. So let's make this explicit. For theta partial over partial theta b, what does that mean? It means if I have something in my exterior algebra, say, I don't know, theta a, theta b, I'm just kind of getting rid of the theta b. And we're just kind of crossing that out. That's what it means to take a derivative in this supersymmetry land. It means we basically get rid of that coordinate. Yeah.
Did you stick a minus sign there?
Because I'm alternating.
You swap yeah.
Yeah, let's do that. Or partial over partial theta b, theta a equals partial over partial equals just theta a. Sorry like that. Yeah.
To understand what vector fields and R2 field. Should I think of it as derivations of this ring you wrote down? Super derivation. Yeah, same thing.
Okay, let's talk about vector fields. So we have, let's move this over here. So we have a little chart down here. So we have vector fields. Abstractly, so says Eric, these are super derivations. Explicitly, I can just literally write them, right?
You do 2 and then 3 bar 2, right?
Yes, V-bar, thank you. These are super derivations, but explicitly, I can write them in coordinates. And when you write them in coordinates, things get much simpler. Basically, what coordinates do I have? Well, I have them up here. It's, vector fields in R2, 1, ordinary vector fields. And then I am sort of, so R2, 1, which I write as, I don't know, sum of Fi for my vector x times partial I. That's some vector field. And then I add on parts that have to do with the other coordinates. Gi times theta 1. Partial I, basically I can add in thetas for all of these. And then I have things that act as with this derivative here. So I have so basically, this is all of the space derivatives where you can add like sort of supersymmetric terms in there too. And then we can also add, maybe H A and then partial over partial theta A and so on and so forth. But explicitly in terms of coordinates, these are things that are relatively simple to work with. You just have to remember that theta, there's a couple thetas in here because this S is 2-dimensional, but the thetas satisfy the Grassmann relations. And the derivatives of thetas follow the rules, some prescribed set of rules. For example, when I take the derivative with respect to theta, I just kill the theta. So we're essentially thinking about functions on this space as functions whose power series has at most one theta term in each part. That's just another way to think about the functions on this space.
This is what I have like theta 1, theta 2, partial deck theta 1. That's
Yeah.
So it's an odd derivation because there's like 2 thetas and 1 like ED theta. So you get like 3 like odd things.
super derivation is also like great.
Yeah, so you can they can direct some of the even ones with the odd ones, and the odd ones satisfy like a super Leibniz rule.
Okay.
Cool.
What is the A and B?
So
Well, we have I and J and A and B.
So let's write this down. So I comma J indices in R21. They are real indices. And we're using A comma B as spinor indices, what physicists call them.
So then the point is, so if we start with, like SO21 is supposed to have 3 generators, which are labeled by like a pair of I and J not equal to each other.
So this is a 2-dimensional representation. Remember, the spinor representation is a 2-dimensional representation of SO2 comma.
But if I give you, say, I equals 1, J equals 2, then what does this element here look like? Like, am I supposed to figure out that there's a certain B and an A that I need to take? Or
That's a good question.
Wait, is this acts on each? So there's like some number of S stars in our exterior algebra, and then this thing will act on each of the S stars.
So we're doing this n equals 1 case right now.
Okay.
But 1 S star. But you can extend this to multiple S stars. They just don't interact with each other. You just add on 1 term for every S star. So the question is basically, you give me an element of this, what vector field do you get? And the point is, it's sort of we're representing this, the action. So basically, every element of this acts on, if we can exponentiate it to give an action on R21. And if we take the derivative of that action, we get this vector field on R21. We can also exponentiate it to get an action on S star. Take a derivative of that element, and we get an element, that we described like this. So I guess I should put, so the explicit A's and B's that you choose, I guess it depends on the specifics of the representation in a way that I'm not sure I can write down right now. But again, what this is meant to communicate is the following. I'm going to call this the spinor. It's like a rotation, but it's really the spinor representation.
Should AB just go from one and two?
So the question is that AB goes to 1 to 2. That does give all of the vector fields here. The question is, if I give you an element of SO21, how do you know which AB it is? Yeah. And it's a two-dimensional representation, so there's 2 degrees of freedom. So AB going from 1 to 2 works perfectly. It's either A is 1, B is 2, or yeah. So don't remember if I wrote this myself or if I stole this from a reference. But the bottom line is, modulo the details of how this form works. These are, again, relatively heuristic, because if I wanted to write this out formally, I'd tell you what the generators are explicitly and where they map and stuff like that. But the heuristics is that a rotation rotates both the base space and the associated spinor. Basically, we're saying that the odd part transforms under the supersymmetry by this representation, and we can write that as a differential operator on superspace, where the differential operator looks at specifically it acts on specifically the part that comes from the exterior algebra of the spinor representation. Okay. So the sort of the main thing here is, what does the supersymmetry do? How does the supersymmetry part actually act on superfunctions? What does this derivative look like? This will tell us what supersymmetry looks like. And let me write it. I can write it. So remember, A is my spinor index. So I have A goes from 1 to 2. And DA is the action of my generator, say QA. I have 2 generators and I get 2 of these actions. And what I do is I differentiate in terms of theta, and I subtract off the following, where I have this A, this is this pairing wrote in indices. I'll describe what that means in particular later. Gamma AB, beta B, particle mu. So, where this represents, so invariantly, what I'm doing here is I am taking this last part here. I can think about that as summing partial in a direction, which, if I take this is a vector in the tangent space, I take that and I do the Clifford multiplication. That's from that pairing over there. You think of this vector as an element of the Lie algebra, of the Clifford algebra, and then you act it on the spinors. And we act this on theta. And there's another way of writing this operator, which is like, again, what you should think of is if you've seen spin stuff before, this is basically a Dirac operator. Okay. So this vector field here is the indices version of the invariant construction, where you take the vectors thought of as tangent vectors in Rn and act them on the spinor space. Okay. Here's what you should notice about this. This is like a rotate. Remember, rotations are you have an x coordinate and a derivative coordinate, and you subtract their difference. This is like almost you take a coordinate in real, and then you multiply it, you take its derivative, and then you multiply it by a spinor. And you take a spinor, and then you add that to the derivative in the spinor direction. you should think about this as rotating. Again, this is schematic, but rotates S star into R2, 1. That's the schematics of this. Yeah, awesome.
Is that a minus sign between?
This is a minus sign between those two. Yes.
And then I don't understand this notation. What is?
So this notation in the invariantly part?
Well, no, on the left. So you're just like.
Yes.
So there's an A and there's a B.
Yeah. So the
So what does this mean? I don't know.
So what this means is essentially, this is a tensor. This tensor is the tensor coordinates of that pairing that I wrote down over there. Okay. So that pairing that takes two spinors and sends it to a vector. That's what these are representing. Now mu here,
It's like a sum over 1, 2, 3.
yes, so we're summing over 1, 2, 3. So we're summing over the space coordinates, and then we're summing over the coordinates 1, 2, the coordinates of S star. That's the A and B.
Oh, okay.
We're summing over those coordinates, we're summing over 1, 2, 3 for that, and we're getting a something as a result.
And theta upper B is the coordinate on the super space.
Beta upper B is the coordinate on the superspace, exactly.
Got it.
Okay. Since it is time, I will finish with the punchline without saying why this is true. But basically, we have an explicit representation in terms of differential operators. The differential operator dA is something which rotates and mixes together both real space and superspace. So we get the following. We can compute this out. We can figure out what dA does. We can just take this and explicitly write what dA squared is. And what we get is something that is basically. Thank you.
Maybe you want the one that isn't.
Yeah. Well, it's 402.
Then we
which
just
means-
have translations, and that's not fun.
No, then we have no symmetry.
So we can take the square root of translations using supersymmetry, which is exactly what I'm doing on this chair right now. We get that dA squared is equal schematically to a derivative. Basically, I have an explicit formula for how do these transforms look as vector fields, and I can apply that vector field twice, and it rotates first from real space into superspace, and then again from superspace back into real space, and ends up as just a translation.
What is mu?
Mu is, right, that's not in here. It's actually, what you actually get is gamma A mu partial mu.
So this is a translation of a particular.
DDX.
So partial mu is translation. I used partial I here. I should have kept that consistent.
No, so this is some translation in some direction.
It's a translation in a direction on the R21 base space. You know, the sort of non-supersymmetric parts. The parts that make sense. Okay.
Right. Can you tell me what that direction is? Is it hard?
Oh, that's the direction. You kind of, I don't know explicitly what it is for each A and B, but you basically look at the formula for your pairing and get it using this formula.
Okay. Maybe it has to do with just. Okay, sure.
But yeah, so that's all I have time for today. This is basically motto. Is the supersymmetry is the square root of translations. Where I would go with this is I'd say that this furnishes a representation in terms of superfunctions. These superfunctions are your superfields, and this is what we actually do and play around with when we actually do supersymmetry stuff. Next week, Chef is going to talk about sigma models and stuff. So yeah, awesome.
So you're